Okay, so to get started with, today we're going to look at the derivatives of y equals e to the x and y equals the natural log of x, or natural log of u and e to the u. But what we're going to use later, just to expand, just to warm up here, is we're going to have to expand logarithms. If you remember, some of our properties of logs were as if you had a product inside a logarithm, you could write it as a single log plus a single log. Or if you had division, you could write it as a log minus a log. What that's going to help us do is, it's going to allow us to take some function that contains a logarithm, make it much, much simpler, right? And then once it's much simpler, then we can go ahead and take its derivative. So with this one, it's the natural log of 3x squared. So 3 times x squared, we can write that as the natural log of 3 plus the natural log of x squared. Then the last step we can do is if you have an exponent inside a logarithm, you can pull it out as a multiple. So you could say the natural log of 3 plus 2 times the natural log of x. Right, that would be one easy derivative to take. Be a good one. Okay, this next one here is we have the natural log of 2x squared over x plus 3. So we do have a quotient in there, and we know that for a quotient, we'll take the log of the top. Again, these are all natural logs, minus the log of the bottom. It's a good chance in your calc class next year too, they'll just refer to it as log instead of natural log because we use it so much. Now here, we still have a product here so we can split it up just like we did our first example. If you have a sum like this, x plus 3 inside the logarithm, you can't do anything to simplify that. It is expanded already. So here we're going to get the natural log of 2 plus the natural log of x squared minus the natural log of x plus 3. And then we'll pull the 2 outside, the natural log of 2 plus 2 natural log of x minus natural log x plus 3 is how we could expand that to get that to be worked out.
Yes. At the beginning, could you also do the quotient rule, or would that not work?
No, don't, because we're not doing the derivative. There's no derivative, we're just expanding.
Okay.
If you didn't expand it and you tried to just do the derivative right away, you would have to do the quotient rule.
Okay.
So this will avoid us from having to do the quotient rule, which is usually a good thing to avoid. Okay, so let's look at how we can find the derivative of y equals e to the x. Just going to kind of show you the reasoning behind it. You don't need to repeat this, and actually we're not going to get super intense on the one step here. But one way, well, the original way that we knew to find derivatives was to use the limit definition, right? So the limit definition would be the limit as h goes to 0 of e to the x plus h minus e to the x over h, right? Again, I just took the function, replaced x with x plus h, and so on. Now, as you look at this, you might, hopefully you notice, e to the x plus h, remember if you multiply a base times the same base, you add the exponents, correct? So this can be rewritten here as the limit as h approaches 0 of e to the x times e to the h minus e to the x over h. Again, just to confirm, all I did here was e to the x times e to the h. We know that's e to the x plus h. So what's going on there? So again, this is not something that you're expected to find here. This is just how the proof works. What we can do is, if you notice, there's a common factor of e to the x on top and bottom now. So with that, we could say this is the limit as h approaches 0 of e to the x times e to the h minus 1 over h. And you still, I'm thinking that doesn't look very clear. But this is a product, and here we're going to use some limit rules that we haven't done much with limits really in terms of the algebra. But what we're able to do is, because this is the limit as h approaches 0, it doesn't have any impact on e to the x because it's h approaches 0. So I can actually pop it outside and say e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now, this is the limit that it has a value of 1. If you graph like e to the x minus 1 over x, you'll see that it looks like it's going to be 1. We don't really have the mathematical desire or skills to actually prove it thoroughly, right? We're gonna leave that to someone more advanced than us. So what we get here is e to the x times 1, which is just equal to e to the x. So again, coolest derivative ever. The derivative with respect to x of e to the x is just e to the x. Okay. Again, this limit goes to the value of 1. I would graph it to check it. We're not going to do the math on that. Or a rule in terms of u is if we have, get rid of this stuff. If we have the derivative of e to the u with respect to x, so for our rule, remember rules will usually have a u in there to remind you of the chain rule. It's just the derivative of itself, so it's e to the u times du dx. So again, really, really nice, simple, very likable derivative. Let's look at a couple examples then. Okay, so our first example here that we all worked on was the derivative with respect to x of e to the x plus x squared. So with this, the easiest way, now I know you could write this as e to the x times e to the x squared and all that stuff. We could, but we don't need to because we have this property here. It just says our derivative is going to be exactly what we started with times the derivative of the exponent. So that tells us that here we're going to get e to the x plus x squared times the derivative of x plus x squared, just to really be thorough there, right? Just using the chain rule. And that's going to be 1 plus 2x. So I would probably write this as 1 plus 2x times e to the x plus x squared. And there we go. Yeah, pretty straightforward. No need to distribute anything. Just kind of leave it be. You're not trying to solve for, all the crazy distributing happened with implicit trying to get the dy dx's by themselves. Here it's already by itself. So we're good. That's it. Okay, let's look at this second example. A little more going on here. We have y equals x squared e to the x. So that is a product, correct? Now this is this is u, and you'll know we could probably do that without writing out all the u's and b's, I would guess. And then here, it's subtracted, so be careful, but it is still a product. So it means both of the pieces we get from this product, the uv prime and the vu prime, will both have a negative in front of it because of that negative sign. So for this one, and again, if you want to write out u and v and all that, that's fine. But I would just go ahead and say that u is x squared. So u, and then v prime is just the same as v, correct? So it's going to be x squared e to the x. Now we'll take the derivative of x squared, which is 2x times e to the x. And then minus, so here we'll take x times the derivative of e to the x, which is just e to the x. And then minus the derivative of x, which is 1, times the derivative of e to the x, which the 1's kind of unnecessary there. I'm looking at these two are actually like terms. They have the same variable exponent part, that x e to the x. So we could say dy over dx is x squared e to the x plus x e to the x minus e to the x is one way you could write that. That's good. A lot of times with these, we end up doing this, though. Our answer might be more useful because we notice each term has an e to the x. If you actually factor it out, then you get x squared plus x minus 1, which may be more useful if you had to find zeros or things like that. But either one of those is fine. Okay, any questions with that? Seem pretty reasonable? Was it one of the best derivatives ever? I think it's right up there, right? Top 3.
Easily.
Okay, now that we know how to find the derivative of e to the x, or e to the u, it's going to make it really easy to use implicit differentiation to find the derivative of the natural log of x, or the natural log of u, if you want to think in terms of that. So, to do this should make sense, I hope. If we start with this function, right, our goal is to find dy over dx. It's to find the derivative of y with respect to x. I don't know what the derivative of natural log is, that's why I'm doing this. But I do know then if this is a logarithm, I can write it in exponential form, correct? I couldn't find the word there. You can write it using exponents. So what's the base down here? If it's a natural log, is e, correct? So we could say e to the y power equals x. We should know how to switch those. Now at this point, I'm going to take the derivative of both sides with respect to x. So the derivative with respect to x of e to the y, the derivative with respect to x of x. So that's just going to give us e to the y times dy dx equals 1. And then d to the y, or dy over dx is 1 over e to the y power. But we, just like we saw with our inverse sine and inverse tangent, we don't want to leave an e to the y in here. But if we look up here, what's e to the y equal to?
X.
It's just equal to x. So we get the derivative of y with respect to x is just 1 over x. So that means that the derivative with respect to x of the natural log of u is 1 over u times du dx. Now we know that 1 over u is u to the negative 1 power, correct? Like for me, this fills in a gap because I always think about, does that rule make sense to us here? How we derived it? But I really feel like it fills in the gap because if I think about, like say I have y is a cube, correct? Y is x cubed, and then y prime would be 3x squared. And then y double prime would be 6x, and then y triple prime is 6. It's kind of silly. And then y 4 primes is 0, correct? Notice the powers decreased by 1 each time, didn't they? But it can't make the jump to get negative powers, right? Because if you have a first power, it becomes 0. So the way you get a negative 1 power is you have to be looking at the natural log, right? So if you take the derivative of natural log, that gives you 1 over x, or x to the negative 1. If you took its derivative, now if you had x to the negative 1, you take its derivative, you get negative x to the negative 2, right? It just kind of picks back up. So this is the missing link, I guess, of derivatives. All right, example here. This is where, for these examples, is where that warm-up we did, where we expand them, is going to make it so much easier. So let's go ahead and I'll show you one here. So we have find dy dx if y equals the natural log of 12 over x. Now this wouldn't be terrible, but you don't just want to grab this rule right away and apply it, because what would happen is you'd get 1 over 12 over x, which we could simplify. It's just x over 12. Then you take the derivative of this, which would be like negative 12. It would just be kind of messy. It's not impossible. It's very possible. You can do it. But I want you to notice here is if we use our expanding properties for natural log, this is the same as y equals the natural log of 12 minus the natural log of x, correct? So now if I want to find the derivative of y with respect to x, I take the derivative of each term with respect to x. So the derivative with respect to x of y, the derivative with respect to x of the natural log of 12, and the derivative with respect to x of the natural log of x. So the left side, I've just shown lots of work here, is dy over dx. What's the natural log of 12? I don't know. Is it a constant? Sure. What's the derivative of any constant? 0. And then minus, what's the derivative of the natural log of x? 1 over x. 1 over x. So we get the derivative of y with respect to x is negative 1 over x. Now, however else you may have tried this way I'm sure is easier, right? I mean, it should go pretty quickly there. The next one I wanted you to try here, and we'll come back and look at it, is go ahead and try to find the derivative of the natural log of x to the 12th over x plus 2. Okay, so give that one a shot there in your notes, and we'll come back and take a look. Okay, so here's our fourth example. Y equals the natural log of x to the 12th over x plus 2. Now do be aware, if you didn't expand it first, it would still work, but you're going to have a mess, right? When you do 1 over the argument, you'd get that to flip, then you'd have to do a quotient rule, and then, yeah, that doesn't sound fun. So let's not do that. So we're going to find derivative of y with respect to x, but first we want to expand this and make it nice. We want to get as easy of logarithms as we can before we take the derivative. So we get y equals the natural log of x to the 12th minus the natural log of x plus 2. Now here, don't forget, we can also plop this 12 out. Makes it a lot easier. Right? Otherwise, you'd have to do 1 over x to the 12th and do the chain rule. So let's say 12 natural log of x minus the natural log of x plus 2. Okay, now at this point, let's go ahead and take the derivative. And note that we're just saying y equals the whole way here because we haven't taken the derivative yet. So once we take the derivative, I'm going to say dy over dx is 12, because that's a constant multiple, times 1 over x minus, there's nothing multiplied, so 1 over x plus 2. Now the argument is different, but what's the derivative of x plus 2? It's just 1, right? So we don't even need to put a times 1. Be careful, it was like a 3x plus 2. You'd have to take its derivative and get a 3. So maybe I should change the example a little bit later. And then what we're going to get here is dy over dx is 12 over x minus 1 over x plus 2. That's great. That's all you get. The one thing I kind of mentioned here, just to clarify, so I guess this is, we'll call this example 4 prime, because, you know, it came from example 4. So we got all these symbols now, right? So what if we had y equals the natural log of 3x plus 2? Just be careful taking its derivative. It's not very tricky, but we'd still get 1 over the argument, which would be 1 over 3x plus 2, but then we take the derivative of 3x plus 2, which is actually 3, right? So you get dy over dx is 3 over 3x plus 2. So just be careful. Something I tend to do is to forget to do the last, you know, the last little chain rule bit in there. So just be careful with that. Again, if you're not, to clarify here, that's the argument prime, which is times 3, and then dy over dx equals 3 over 3x plus 2.